Okay, one more video on rotational motion, one more numerical on rotational motion. Right, let us see what we have over here. A cord is wound around the circumference of a wheel of radius 0.5 meter, and 2 kg mass is tied to the free end of the cord and allowed to fall from rest. Right. Okay, so we have a situation something like this. This is, let us say, for example, this is the, let us say, the circumference of the wheel. Right, this is the wheel, and let us say we have a rope which is a cord like this, right? Cord is wound over here like this. So, and we have a 2 kg mass over here. So this is 2 kg mass tied to the free end of the cord, and it's allowed to fall from rest. So this mass actually would be over here, and it would be allowed to fall from rest. So here the velocity of this particular mass would be 0 because it is allowed to fall from rest. Right? The axle of the wheel is horizontal. The axle of the wheel is horizontal, meaning the axle of the wheel is perpendicular to the plane of the paper. As you can see, the way I have put the marker, right, perpendicular to the plane of the paper. So the axle is going inside the plane of the paper, and this wheel is rotating like this in the vertical plane. The wheel is rotating in the plane of the paper. The axle is going into the plane of the paper, and the rope or the cord is put up like this. The mass falls 4 meter in 10 seconds. So this mass, when it is released, it falls 4 meter in 10 seconds. 4 meter in 10 seconds. Find the angular acceleration and the moment of inertia of the wheel about the axle. So I have to find out angular acceleration of this wheel and its moment of inertia. G is to be taken as 9.8 meter per second square. Okay. So let us first try to understand how we will be able to find out angular acceleration of the wheel. So we have this wheel over here. Its angular acceleration, right, it would be obtained if we are able to find out the linear acceleration of this wheel at this particular point, right? For example, we have this equation A is equal to R alpha. Right? I want to find out alpha, angular acceleration. So I know radius R. This radius is known to me as 0.5 meter. If I know the linear acceleration of this particular point, then I can divide it by R and get alpha. What is the linear acceleration of this particular point of the wheel? Right? The wheel is performing circular motion. What is the angular acceleration? What is the linear acceleration of this point? The linear acceleration of this point of the wheel would be equal to the linear acceleration of this particular rope. Right? This rope, when it falls down, is trying to take this point of the wheel downwards in a linear direction. Right? That would be its linear acceleration. And if I multiply it by, or divide it by R, I would get angular acceleration. So what I'll try to do is I'll try to find out the linear acceleration of this particular row. It is going down 4 meter in 10 seconds. Right? Now we know that the initial velocity is 0. Right? Now we have this equation. Let us say S is equal to ut. Let me use this space. S is equal to ut plus half at square. Initial velocity is 0 of this mass. So I'll get S is equal to half at square, because this term will become 0. Is equal to half into A, or let me write S is 4 meter, is equal to half into acceleration in 10 seconds, 10 square. So I will get 8 is equal to 100 A, therefore A will be 0.08 meter per second square. Right, so I have got acceleration as 0.08 meters per second square, and then alpha is equal to A upon R, 0.08 upon 0.5. R is the radius of the wheel. Therefore, alpha is equal to 0.08 upon 0.5, and that would give me 0.16 radians per second square. So I have found out angular acceleration. Now we have to find out moment of inertia of the wheel. Right? One of the equations for finding out moment of inertia is tau is equal to, for example, if tau is equal to I alpha. I know the angular acceleration of the wheel. Right? If I am able to find out tau, then I will be able to find out moment of inertia. So now what I will try to do is finding out tau. What is the torque acting on this wheel? Torque. Who is applying the torque? Or what is the agency which is applying torque on this wheel? It is this particular force. The gravitational force. When the mass falls down, the earth is pulling it downwards. It is that force which is acting over here. And what is the magnitude of this force? Right? We'll try to find out that. Coming back over here, torque is equal to force into R. The force applied over here, right? The net force over here, I'll call it F net, applied over here into this particular distance R. That is the torque applied over here. So now the objective is to find out F net. Now what is the F net acting over here? The total force acting is this gravitational force. This particular gravitational force is being used for two things. One is for acceleration purpose, for accelerating this downwards, and for applying this torque. So I'll write over here total gravitational force is equal to, it is applied for applying for acceleration or I'll write accelerating force plus torque, meaning the force applied for, force used for applying the torque, not exactly the torque. Let me specify over here, force for torque. Right? Total gravitational force would be mg, right? Accelerating force would be ma, plus this would be the force of for torque. Let me call it F net over here. Right? So F net would be m into g minus a. M is 2, 9.8 minus acceleration. A we have already obtained as 0.08. And if I do this calculation, 9.8 minus 2.08, let me do that calculation quickly. 9.8. I'm sure you are with me and you're also doing this calculation. Multiplied by 2 would give me 19.44 Newton. 19.44 Newton. And then I can have torque is equal to F into R. So 19.44 into R is 0.5. Multiplying by 0.5 is like dividing by 2. So I divide by 2 will give me the torque that I will obtain will be 9.72 Newton meter. And now I will use I is equal to torque upon alpha, 9.72 upon alpha I have obtained as 0.16. So 9.72 divided by 0.1 divided by 0.16. 9.72 divided by 0.16 will give me 60.75. 60.75 kg meter square. So I is 60.75 kg meter square. Right. So we have obtained both alpha and I. The point I want to revise or once again stress upon is the fact that how we converted or how we handled linear motion and rotational motion, and how this particular force we use to find out torque, and how the linear acceleration of this point of the wheel is connected to the rotational or the angular acceleration of the point of the wheel. Keep these points in mind when you are trying to solve any other numerical on rotational motion. See you in the next video on rotational motion. Thank you.